Assalamu alaikum and welcome to lecture number 22. In this lecture we are going to discuss briefly about the filters and the filters described by differential and difference equations. In the previous lecture we talked about the response of LTI system to complex exponential, and we showed that response of the LTI system to complex exponential input is the same complex exponential with only change in the amplitude. That is, if input is complex exponential, then the output is h of s times the complex exponential, and we call the h of s as the frequency response when s has a real component equal to 0, so that is h of j, that will result into h of j omega, and we call it the frequency response of the LTI system. So we understand that h of j omega is basically frequency, function of omega, and the output, which is equal to h of j omega times the input. So the output changes with the j omega, or simply with omega. So taking the same concept, in this lecture we are going to talk about the filtering. So filtering is defined as a process through which the relative amplitudes of the frequency components in a signal are changed, or a component is eliminated entirely. So we have two types of filtering. One we call them the frequency shaping filters, and the other we call them the frequency selective filters. In case of frequency shaping filters, the LTI systems change the shape of the spectrum. For example, in the audio system, the LTI filters can modify the relative amounts of the low frequency energy, or they can modify the high frequency energy. So we will not talk about the frequency shaping filters, but we will talk more about the frequency selective filters, which are defined as the system that are designed to pass some frequencies and significantly attenuate or eliminate other frequencies. So such frequency filters, selective filters, have different applications. These include communications like the radio or the television communication systems. They include the frequency selective filters. So these filters are basically classified into three categories, namely low pass filter, high pass filter, band pass filter, and for example, one more category can be the band stop filter. So here the important thing is the cutoff frequency. So cutoff frequencies are basically the boundaries between the frequencies that are allowed to pass and the frequencies that are stopped. Shown in this figure on the left side are the filters used in the continuous time systems. So the shown here is the spectrum of the low pass filter. So it can be observed from here that low pass filter passes frequencies between 0 and the cutoff frequency, which is omega c. Up to this range it passes, both for the negative case also, that is 0 to minus omega c, right, where omega c is the cutoff frequency of the filter. and these responses are the ideal one, right? So below cutoff frequency the signals are passed, and above cutoff frequency signals are stopped. So similarly for the negative case. So this is an example of the low pass filter. So we can say a low pass filter has one pass band and two stop bands, right? Omega C, and above they are one stop band, and similarly minus omega C, and below this they are another stop band. Whereas from minus omega C up to omega C, this is the pass band where the low pass filter will pass the signals. Similarly, for a high pass filter we have one stop band, right, and the one pass band. Pass band is from omega C up to infinity, right, and here also from minus omega C up to the infinity, right? So from minus omega C up to omega C, this is the stop band of the high pass filter, right? So all those frequencies that are greater than the cutoff frequency is marked here with omega C. So all those frequencies that are greater than omega C are passed, or all those frequencies that are less than minus omega C are passed. Similarly, in case of band pass filter, this is the figure showing the band pass filter. So for the band pass filter we have two cutoff frequency, one low cutoff frequency and one high cutoff frequency, right? So the frequencies between omega C1 and omega C2 they are passed, whereas frequencies between omega C1 minus omega C1 and minus omega C2 they are passed, whereas those frequencies that are lower than minus omega C2, that is this side, they are stopped. So this is the stop band. Similarly, the frequencies, right, or in general we can say the signals having frequencies of from minus omega C1 up to omega C1, they are stopped. Similarly, frequencies greater than omega C2, right, all those signals that have the frequencies greater than omega C2, they will be stopped. Similarly, for the case of the discrete time signal, which are shown here on the right hand side, so similar argument applies, right? So I hope this is clear to you that also in case of the discrete time signal, the frequency is between minus omega C up to omega C. This is the low pass filter, and these frequency signals having these frequencies, they will be passed, whereas frequencies greater than this are stopped. So you can observe that the response of the low pass filter in discrete time case, in fact all the filters, they are periodic. So you understand, if you recall that we said the discrete time signals cannot have frequencies greater than minus pi r plus pi, right? So because you understand, when we increase frequencies of the low pass of the discrete time signals, right, they increase from 0 up to pi. So the maximum frequency they can have is pi. Beyond pi they start decreasing, and they have the same frequency at 2 pi as it has at the 0 and multiple of 2 pi, right? So we normally say that from 0 up to pi are from 0 up to pi, or from 0 up to minus pi, these are the highest frequencies for the discrete time case, right? And we also say that frequencies at the integer multiple of odd pi, right, at the integer multiple of odd pi are those signals that have the highest frequencies, and the signals having frequencies near 0 or near the 2 pi, they have the lowest frequency and they are same. So you can see again here that because this is low pass filter, so it will pass the frequencies between 0 and omega C, or between 0 and minus omega C. So similarly, because they have the same frequencies at 0, right, so at 2 pi again we see, so the response is also periodic for the discrete time case. Okay, so a similar argument applies to the high pass filter. You understand, the frequencies start increasing and they reach at the maximum level at pi. So the frequencies around the pi, they are the highest frequencies, and as you move from the pi, the frequencies start decreasing, and at 2 pi they have the same frequency as at the 0. So that means the pass band of the high pass filter, it will be around the pi, right? So it will repeat, like it will be it is around pi, then it will have around 3 pi, around 5 pi, around 7 pi, and so on. Similarly, in the negative case, the frequencies, the high frequencies are those that around are minus pi, around minus 3 pi, around minus 5 pi, and so on. Similar argument applies to the band pass filters in the discrete time, right? So in general, you understand that in case of filters responses in the discrete time case, so the responses of the filter, they are also periodic, right? So in the part C on the right side here, it is shown the ideal graph for the band pass filter. So you understand these are the frequencies, right? This is the lower cutoff frequency, and this is the higher cutoff frequency. So the response is also periodic. So let's consider the ideal low pass filter. So the ideal low pass filter have frequency response, right? You understand this is your omega axis, and you understand that we are in frequency domain, because in frequency domain the independent variable is omega, right? So on the x-axis we have omega, on the y-axis we have the response, in contrast to the time domain where we had on x-axis as t. So for example, this is the frequency response of the low pass filter, this is the cutoff frequency, and we are considering the ideal case, right? So mathematically this can be written as h of j omega has value, right? That's the absolute value, that is the response, right, or magnitude response. So h of j omega will be equal to, if we look at this one, for example, this is 1, so the amplitude is 1, right? So this is the frequency, this is equal to 1 for the frequency, absolute frequency let's take, because this means if absolute frequency is less than or equal to omega c, that is whether it's a positive or negative. If it is in this range, this is equal to 1 and it will be 0 otherwise, right? So you can observe the sharp response here, right? This is for the ideal case. The practical filters, they don't have the sharp curve, rather the fall is something like this, okay? Depending upon the order of filter, we will not go into much detail here, but we'll just talk about the point where the response, right, h of j omega magnitude, right, magnitude response equals to this equal to 0.707. so you understand it is dropping, right, with the frequency, because it's a low pass filter. So if you move from the 0, right, up to a certain range, in case of ideal filter up to omega c, which is its cutoff frequency, it will remain 1 and it drops down within no time to 0. But in practical case, it will gradually drop, and the point where its value is 0.707 is called the cutoff frequency, right? At cutoff frequency, the magnitude will be equal to 0.707, and we call it the cutoff frequency. And the linear case, it will be represented by fc, or in the this case it will be represented by omega c, right? So practical filters are, you understand, you all are electrical engineering students, so you understand practical filters are built from resistor, capacitor, and inductor. So if we talk about the first order filter, the order means the number of capacitive and inductive devices included. So in case of first order filter, you can make it either from resistor and capacitor, or you can make it from resistor or inductor. So let's take the previous example like we had. So cutoff frequency is basically equal to, in case of RC filter, let's draw an RC filter here. So this is your R, right? It may not look very good, but okay, you can see it, right? So it seems like this one is your R and this is your C, right? So the cutoff frequency FC equals to 1 over 2 pi R into C, or you can also take this term to this side, so that it will be equal to 2 pi times the FC equals to 1 over RC R. You can also say that because this is equal to omega C, right? So omega C basically equals to 1 over RC, right? So the frequency of the filter is basically calculated based on the values of the R and C. So what cutoff frequency this will have is basically equal to 1 over RC, right? For example, R equals to, right? R equals to, for example, 10K, right? And C equals to, for example, 1 nanofarad. So what will be the cutoff frequency of this circuit, right? So it will be omega C will be equal to 1 over 10K into 1 nano. 1 nano is basically 10 power minus 9, right? So it will be 10 power minus 9. So this is K. So this will be minus 6, or if I shift it upside, so it will be 10 power plus 6, 10 power plus 6 divided by 10. So it's something like 100, right? Is it 100, right? 100 kilo, and the unit will be radian per second, right? So because we have done the we have considered an example of this circuit in the previous lecture, so we found that h of j omega equals to how much? In this case it was 1 over 1 plus j omega RC. So this was the frequency response of this circuit. What if I want to make it to a high pass filter? So you understand high pass filter can be made in the same way. If you understand this is low pass, right? Because the output voltage we are taking is from the Y of C, right? So you understand, as the frequency of, for example, input is x of t. So as the frequency of the input signal increases, what happens? When the input signal has zero frequency, we have this will work as a open circuit, and all the voltage will appear here. So the output or input will be equal to 1, right? And no. Right? So as the frequency of the input signal increases, the voltage drop across the capacitor will start decrease. Why? Because frequency and the capacitive reactance, the resistance of the capacitor is basically capacitive reactance, and they have the inverse relationship, right? So the capacitive reactance is x of C equals to, so the capacitive reactance is basically xc represented by xc, and it is equal to 1 over 2 pi fc, right? Or 2 pi f, this can be replaced by omega, so it has 1 over omega into C. Omega is C is constant, right? Capacitance, so xc is inversely proportional to omega. So as the input frequency increases, right, the capacitive reactance will decrease, right? So that's why at very high frequency the capacitive, right, at very high frequency, say omega equals omega equals to infinity, so Xc will be 0, so that means the voltage drop, because you understand voltage across the capacitor is equal to current times the Xc, so Xc will be 0, so that means there will be no voltage drop across it. So that means, because we are taking the voltage from the here, right, we are taking the voltage from the capacitor, so that means the voltage drop, if here is voltage across capacitor is 0, so that means the output will have very low voltage. So I hope you understand that as the frequency increases, the inductive reactance, the capacitive reactance here decreases, so resulting in reduced voltage. So that means as the frequency of the input signal increases, the voltage here will decrease. So that means this is why the response is like this. And you also understand that the cutoff frequency is basically determined by this equation. So depending upon the value of R and C, we can select the capacitive, we can select the cutoff frequency. Similarly, if I make the high pass filter, so high pass filter will only be just replacing the values of C and R, that is, so I have replaced just R with C. So now we are taking output from R and C is here. So you understand, when the frequency at 0 frequency, all the voltage will be dropped here, and there will be no voltage across R. So that's why if I make the magnitude response for the high pass filter, it will be something like this. You understand, at the right, this is the similarly for the negative frequencies, right? So for ideal filter, it will be something like for example, this is the cutoff frequency, so ideal filter will have response something like this. Okay, so this is the cutoff frequency, for example omega C. So the ideal filter will have response equal to 1 beyond this, but practical filter, it will be something like this, that maybe I just make it like, right, it is something like this. So this is the cutoff frequency. At cutoff frequency, it will have a response it will have something like this, right? This is the practical. So do you think, do we need to change the values of R and C, or we should use the same, right? So that depends upon what is your cutoff frequency, right? So if your cutoff frequency is same as here, like for example here it is 100 kiloradian, right? So if you want to have a 100 kiloradian, then for the low pass it will be like this, and using the same component for the high pass it will be something like this. So you understand why this is so. Okay, so similarly, combining the low pass with high pass, we can make a band pass filter. So let's discuss the filters described by a differential or difference equation. Right, so we have a circuit which we have already discussed, that is, this is the source voltage or the input signal, and this is the output voltage or the YCT, and this is R. So this is, if you look at this one, you understand this is a low pass filter. Why this is a low pass filter? Because as the frequency increases, the voltage across here will start decreasing. So this is a low pass filter, and why this is so, I hope you understand. So let's the problem is, let's find the differential equation for this circuit, and we need to find the frequency response, also plot its magnitude and phase response, and what is its impulse response, right? So that's very simple, that if we look at this one, so the current flowing here, this is for example IC, which is because this series circuit, so both the R and C have the same amount of current flowing through it. So what is the voltage drop? So voltage drop So what are the voltages here? So using the Kirchhoff voltage law, you can find the voltages here, right? So just let me write here the input voltage is x of t, for example, okay, which is written as source of t. So let me write in the same notation or same. So the input is x of okay, v source of t, right? That's our input, and this is equal to drop across the resistor, which is I CT. Can I write it like this? Because CT emphasizes time varying, right? So ICT into R plus the voltage drop across the capacitor is VCT, right? VCT. So this is the equation, right? Now what is the value of the current? So you understand in case of capacitor, current equals to voltage VCT equals to 1 over C integration minus infinity to T and IC of tau d tau. Okay, now if I take the integration of both differentiation of both sides, then it will be d upon dt of VCT, right? VCT, and this is equal to 1 over C, and this is equal to ICT, or 1 by C. If I bring it to this side, it will be just, can I bring it straight away? If I multiply both sides by C, so this C will cancel with this and it will result into this. So I can just straight away write like this. So this is the value of the current. If I replace it here, then I can find. Okay, so let's replace it here. So we are given the system is LTI, that is linear and time invariant, right? Now for this we have done that if the input is, for example, e power, let's take the, if the input is, for example, e power j omega t, right? For example, this is the input. When this is the input, what will be the output, right? So that is, let me call them V source here. So it is V source of t. If V source of t equals to e power j omega t, so you understand the output will be equal to what? The output will be equal to the same this, but with this scaling factor, right? You understand that e power j omega t, which is a complex exponential, they are the eigenfunction of the LTI system, because whatever you give it to the LTI system, you get the same with some scaling factor, and the scaling factor is h of j omega, right? So that means VCT for this one, which is output, right? So the output will be equal to h of j omega into e power j omega t. Hope this is clear to you, right? Because this is the complex exponential input, so the output will be the complex exponential times the system's frequency response, right? So the output will be equal to frequency response times the e power j omega t, which we have already discussed in the previous lecture. So let's replace VCT with this value, right? So this is our equation. Right? So what will be okay, so if I put this one here, then I get something like this V source. So V source is basically equal to e power j omega t, and this is equal to RC. And what will be derivative of VCT? VCT is basically, you understand this, right? So when VCT is this thing, derivative of this, because this is constant. Why constant? Because we are differentiating with respect to time. So this may be this is treated as constants, right? So that's the, and this one, what is the derivative of this one with respect to time? So e power jt d, if I take derivative, so it will be equal to j omega, right? So it will be something like, if I straight away write here, right, I just write here d upon dt of this thing, so it is equal to d upon dt of this one, right? So this will be e power j omega, right? So this will be treated as constant. Why? Because there is no t involved here. So what is the derivative of this? So it will be e power j omega, right? J omega t, and again derivative of j omega t will be j omega. So this is the derivative of the what? VCT, right? So that means we can write it like, okay, so we were here, now we just replace the value. So the input source is e power j omega t, right? E power j omega t, and this is equal to RC, and VCT is this one, right? So we have done this, right? This is your VCT. So derivative of this, if you look at this equation, right, I'm doing this equation. So if you look at this equation, so here derivative is, if I take the derivative, which if you have already taken, so it will be j omega, right? You understand? And it will be h of j omega, and this is e power j omega t, and plus VCT is h of j omega e power j omega t, right? So if we take j omega t as common from here, right, so that means this one. Okay, so I have already taken this common, so I can remove it from here. So what I'm left with is this thing. Okay, and you understand e power j omega cancels with e power j omega. So on this side we have 1, and this is RCJ omega hj plus this one, right? So we can again take hj omega, right? So if I take hj omega as common, so I have hj omega, and I am left with what here? RC j omega, but okay, j omega RC, and plus it is 1, right? So because I need to find the frequency response, which is h of j omega, so this thing is multiplied here. If I bring it to this side, it will be divided. So hope you understand that it will be something like 1 over j omega RC plus 1, but because we normally write the real part first followed by the imaginary part, so I can write that h of j omega basically equals to 1 over 1 plus j omega RC. So this is the frequency response of this circuit. So if you recall the previous lecture, in previous lecture we were given the impulse response, and using the impulse response we found the frequency response, which is exactly this one, right? Why? Because both are the low pass filters. So when both are low pass filter, you get the same, right? So this, using the differential equation, we found the frequency response, and there we were given the impulse response, and from impulse response we found the frequency response. Okay, so I hope no need to draw the magnitude and phase spectrum for this one, because we have already done this in the previous lecture. So this is as a homework I gave you, right? Okay, so let's find the impulse response for this circuit. So how to find the impulse response? That's very simple. How you find the impulse response? So remind me when we will be doing the Fourier transform. So I will tell you how to take the inverse of this one from, so that, but anyway, from in the previous example we can say that h of t for this will be equal to 1 by RC e power minus t by RC into u of t. So that will be the impulse response for this circuit. So here we have another example, and in this example we have the high pass filter, right? Is it high pass or low pass? So it's a high pass filter. Let me draw the diagram. So again we have the source voltage, which is VST, and this is the capacitor, right? And then we have a resistor here, okay, and R. So this, the output is taken from R, so let we call it VRT, right? So that's the output voltage, and you can easily guess, being electrical engineering student, that this is basically a high pass filter. Why high pass filter? Because at very low frequencies the capacitor will act as a open, and there will be no voltage across R. But as the frequency starts increasing, the voltage across capacitor will start decrease. Why? Because its voltage is proportional to its capacitive reactance, and the capacitive reactance will start decreasing as the frequency starts increases. Okay, so let's first write a differential equation for it. Maybe I gave you as a homework. How about it, right? Because in the previous example you understand, right? So if I write it like this, so maybe if it doesn't take long time, then I'll do it now. Otherwise I'll give you as a homework. How many of you will be saying now do it? Okay, so the source voltage is split between the divided between the voltage across capacitor and voltage across the resistor. So that will be VCT. Let's we call it VCT for the voltage across capacitor, plus VR, which is voltage across the resistor, right? So that's VRT, right? So how to express the this into a differential equation? That's a big question. How? Good. So because now the output is VRT, so we have to express the VCT in terms of VRT. So how to do that? So VCT is basically equal to, you understand, in case of capacitor it will be equal to 1 by C, or let me write it here. So it's VST is equal to 1 by c, right? Integration of minus infinity up to t I of tau, right? Deta plus v r t. So if we take integration of both sides, then it will result into d upon dt of vst, and is equal to ICT, C, right? ICT by C, and plus d upon dt of VRT, right? So because ICT, that is current flowing through the capacitor, is basically equal to, because series circuit, you understand, right? So that means it is equal to VRT by R. So replace it here, and right, replace it here, and then we again assume that input signal is Vst e power j omega t. So hopefully using this expression you can go and you can find it by yourself. Okay, then after doing this, find the magnitude and phase response, and I hope I have in the previous lecture we have explained it, and you can do it by yourself. Okay, so if you have any problem, you can discuss in the live session, but I hope this is quite straightforward and you should do it. So let's consider examples from the discrete time case also. So in discrete time case, we have let's straight away jump to the example, I think. So this is the difference equation for a discrete time system, and we need to find the frequency response of this system. So to find the frequency response of this system, let's first find the impulse response, or you can also use the similar arguments as we did for the continuous time case. So let's assume we have a complex exponential input signal x of n, such that x of n equals to e power j omega n, right? Now when this is the input and we know that the system is LTI, so output will be equal to the right, output will be equal to y of n, and y of n will be equal to h of let's represent it by the capital H of j omega, right, times the e power. Hope you understand, I am just replacing values here, right? So the h of j omega is the frequency response of this system, so output will be equal to, like we define it, the same input but its scaled version. So minus a times the h of j omega. You understand, it will be same h of j omega, sorry, the small one, right, the capital omega here, right, because the system has no effect on, because it's a frequency domain, so h of j omega has no effect, is not affected by, and so this, and then e power j omega n minus 1. Also mistakenly I have written the small omega here, so let me write it as the capital omega. So this is a capital omega, and again this is capital omega, so I'm here, and this is equal to e power j omega n, right? So I can take j omega n common from the both sides, so I am left with e power j omega n. If I take this common, so I have this thing here, h of j omega, right, or minus a h of j omega, right? And if I take j omega n as common, I am left with e power minus j omega, right? And this is equal to e power j omega n, and this cancels with this one. Again I take h of j omega as common, h of j omega common, so inside the bracket I have 1 minus a into e power minus j omega, and this is equal to 1. So that means h of j omega equals to 1 over 1 minus a e power j omega. That's minus, right? So this is the frequency response for this recursive equation. So based on this equation, can you tell whether this is the high pass filter or this is the low pass filter, right? So I'll ask you to assume values of a, right? In case 1 you take it 0.6 and write this your case 1 and then plot this signal. Okay, case 1, take a equals to 0.6, and in case 2 take, right, case 2 take a to be minus 0.6, right? Plot the magnitude and phase response for this difference equation. So that's all for today. See you in the next lecture.